Hello and welcome to another video. In this video, we shall see signal flow graphs. Signal flow graphs are alternative to block diagrams. So we will see a few examples of signal flow graphs, how they help in the perspective of control system. So signal flow graphs are a graphical representation of the relationships between variables in a control system. As I mentioned earlier, they are alternative to block diagrams. In block diagrams, we had blocks, signals, summing junctions, and pickoff points. But here we will have branches and nodes. The systems are represented by branches, and the signals are represented by nodes. The importance in control system is that we can analyze complex systems visually and derive the transfer functions systematically. We will see the formula that we will use in signal flow graphs, and it is also helpful in understanding the feedback loops and interactions. And the key concept here is signal flow graph translates block diagram into interconnected nodes and branches. The basic elements of signal flow graphs are nodes and branches. A system is represented by a line with an arrow showing the direction of the signal flow through the system. Adjacent to the line, we write the transfer function. Now a signal, it is a node where the signal's name is written adjacent to the node. We will see an example where the input is R of S and the output is C of S. And the transfer function is G of S. So in the block diagram, it is the input signal R of S and the output signal C of S and the transfer function G of S. That equivalent representation in a signal flow graph is R of S as a node, C of S, the output is also a node, and the transfer function is shown with an arrow joining between R of S and C of S. So this is a representation of the signal flow graph of the corresponding block diagram on the right. So the nodes represent the system variables like input, output, intermediate signals. The branches represent the transfer function for the gains like G of S, H of S, etc. And the direction is shown how the signal flows from the cause to effect. And the key terms here are the source node, which represents the input, here in our case R of S, and the sink node represents the output. In our case, it is the C of S. We will see a few basic examples how to convert a block diagram to a signal flow graph. We need to identify the input, the output, and the intermediate signals. We need to represent each of these signals as a node and replace the blocks, the transfer functions, with directed branches. So there will be line and there will be arrow mark in it. So this shows the direction. So we have directed branches which replaces the blocks. So we will see a basic cascade block diagram which will be converted to signal flow graph. So this is a cascade system where the input is R of S and the output is C of S, and there are three transfer functions which are kept in series. So the ultimate transfer function will be G1 into G2 into G3. So we will see how this is converted to the signal graphs. The intermediate signals here right after G1 will be V1, which is equal to G1 into R1. And the signal which is right after G2 will be V2, which is equal to G1 into G2 into R. And the output C of will be G1 into G2 into G3 into R. So now we will write the equivalent signal flow graph. And we need to identify the input. Input is R of S, the output is C of S, and the input signals like V1 and V2. So represent these signals as nodes. So we represent it as circles, as nodes here. Blocks, identify the blocks. Blocks are G1, G2, and G3. And this will be represented as directed branches. There's a connection between R and V1 that is by a directed branch, and near to that arrow we will write the transfer function G1 of S. Similarly, from V1 to V2 we'll write a directed branch, we connect it as with a directed branch, and write the transfer function near to it, G2 of S. Similarly, from V2 of S to C of S. So this is the equivalent signal flow graph for this transfer function. Now we'll see another example, the negative feedback system. So here we have the input R of S and the output C of S, forward transfer function as G of S, and the reverse transfer function, feedback transfer function as H of S. Now we are considering a negative feedback system, and this is a block diagram. On the left we see the block diagram representation, on the right we have the signal flow graph representation. So each of the signal R of S, the signal here, that is nothing but E of S, and the signal here, C of S. So each of them will be represented by nodes. So we show it as small circle, each of this as nodes. Find out the blocks G of S and H of S. Now we need to put directed branches connecting all these nodes. Now we have forward loop where R of S and E of S we have with the gain 1, and E of S to C of S we have the transfer function G of S, and for the feedback we have minus H of S. So here you may have noticed that the negative sign is associated with the signal H of S rather than giving it with the summing point. Now the advantage of representing a system in signal flow graph is because of its simplicity of reducing it to a single transfer function. In block diagram, we use block diagram reduction for reducing it to single transfer function. But here in signal flow graph, we use the Mason's gain formula. So we apply that formula and we get the single transfer function. Before going into that formula, we need to understand few definitions. The loop gain is the product of the branch gains by moving a path that starts at a node and ends at the same node. This loop, which starts at this node and it moves forward and there is a return path. So it terminates at this node. So this is a loop. This is an example of a loop. G4 and H2. G4, G5 and H3, and there is another loop G4, G6 and H3. So these are the different combinations of loops. Now forward paths. The product gain found in moving from the input node to the output node. So input node is R of S and the output node is C of S. So the forward path, the first forward path is this, which moves from the input to the output. The second forward path is this. So there are two forward paths here. Now we will see another important concept, which is the non-touching loops. So here, this is a loop and this is another loop. So these two are non-touching loops. Similarly, G2H1 and G4, G5, H3. This both are non-touching loops. Also G2H1 and G4, G6, H3. These two are non-touching loops. So there are many combinations of non-touching loops in this example. So these loops that do not have any common nodes are called non-touching loops. Now the concept, the Mason's gain formula, and how it is used to derive the transfer function of the overall system. The ultimate purpose of the Mason's gain formula is to derive the overall transfer function G for the system. Now the key terms are path gain, the determinant value, and delta K, determinant with subscript K. Here in this formula, suppose we have K number of forward path, Tk is the forward path gain, and delta is 1 minus summation of loop gains plus summation of non-touching loop gains taken 2 at a time minus summation of non-touching loop gains taken 3 at a time plus summation of loop gains taken 4 at a time minus summation of loop gains taken 5 at a time, so on. And delta k is nothing but delta minus summation of loop gain terms in delta that touch the kth forward path. We will see delta and delta k in an example. So we will take the same feedback system which we have seen in the previous slides, and how to derive the transfer function using Mason's gain formula. Now Tk is the forward path gain, that is nothing but G of s. Here there is only one forward path that connects between R of s and C of s. So the gain of that one forward path is nothing but G of s. So Tk is the forward path gain. Delta is 1 plus G of s into minus H of s. That is nothing but 1 minus summation of the loop gains. So here the loop gain is G of s into minus H of s. So this is the loop gain. Gain of, there is only one loop, and the gain of that one loop is G of s into minus H of s. So resulting 1 plus G of s H of s. And delta k is delta, whatever value of the delta, minus the loop gain terms in delta that touches the kth forward path. There's only one forward path, and the loop is touching that forward path. So we need to eliminate this to get delta k. So the value of delta k will be 1. And substituting it in the formula, we get the transfer function as G of s, the forward path, divided by 1 plus G of s H of s by delta. So this is a transfer function. In the block diagram example, we had derived the same transfer function. Here, using signal flow graphs, using Mason gain formula, we have derived this transfer function. We will see a few more complicated examples of application of signal flow graph, deriving it using the Mason gain formula. Thank you.